let's get started. Today we'll quickly breeze through web application development and web services. The whole idea of discussing this part is that now we know how to acquire big data, how to manage big data, but then the missing piece is how to build applications using big data. The key problem comes from interoperability. So let's assume we have several distributed systems and each system has to talk with another. So in such context, we need to have some standard ways that enables us to communicate with each other. Well, there are several rudimentary solutions, like you may consider file transfer. So whatever I want to talk to another system, I just put it on a file and I save it somewhere or transmit over the network and assume that the other system knows how to read the file and make sense out of it. The same can be achieved using a shared DB also. Or if we go a step further, we could have applications running on two distributed systems and one application is somehow able to call procedures on an object which is residing in another system over the network. So that's what we call as remote procedure calls. We could also have some standard ways to communicate between these systems through message passing. So these kind of solutions have become popular. CORBA, DCOM, and RMI are middleware platforms which provide us with all the libraries and the framework that we need to do this RPC and message passing. All right, so the focus of this talk remains on web services, but still for the sake of completion, we'll quickly discuss CORBA, DCOM, and RMI. The idea of having CORBA is to build or to have a middleware such that it acts like a broker to communicate between two systems. So here you see I have a client which let's say requires an object reference and let's say it's calling some method on that object. So all it needs is a reference and then it can just call, and to get that reference it may contact the broker. And similarly on the server side, let's assume this object resides and it's ready to so if a method is invoked on an object, that can get served over here, let's assume. So now we have this client server kind of a setup where a client is invoking a method on an object which is residing in the server, and the middleware enables this interaction. And the component, the component that enables this interaction is the object request broker, and this entire architecture is called CORBA. CORBA is essentially language neutral, vendor neutral standard maintained by Object Management Group, OMG. And it was quite popular and successful in the late 90s. However, the vendor-specific applications like Microsoft's DCOM and Sun's RMI took over very shortly. So here is an example of implementing with CORBA. So how do I start? I start creating something called as an IDL file, which simply says how does the interface of the object look like and what are the methods that anyone could call on them. So in this case, let's say I have an hello interface, and you may call a say hello method, which is expected to return a string. So this is just an interface. It doesn't implement anything. So obviously this is only useful on the client end to invoke a particular method. But of course, we need some infrastructure which would delegate these invocations to the server and have the execution happen on the server end and then pass on the results back to the client, or somehow get the object reference from the server itself so that the invocation can happen on the client. So we need some middleware infrastructure to do that. So the first step is, after writing the IDL file, the next step is basically to compile this IDL. So there is, let's say you're using Java, then there's an IDL2 Java IDLG compiler, which would compile and generate a bunch of Java files. So here is an example. So I have interface from where when I compile, it generates a few class files. So hello implementation is one example of that. So here we see that there is these implementations for say hello and shutdown methods. So I can write a client now. The client simply invokes the broker, the ORB, and tells the broker that it's interested in invoking a particular object or the methods on a particular object. And then the code can continue beyond this, which basically calls those methods. If you're interested in the entire example, you can find it on the docs.oracle.com site, the link of which is given on this slide. And similarly, we write a server-side component as well, which again uses the ORB and tells that, look, here is the class, here is the server's part, here is the implementation, which of whose reference can be passed through the ORB. So that's the whole idea of how CORBA works. So we just basically compile all the files, run the ORBs on both sides, and start the server and the client. And assuming we have the CORBA libraries available on both ends, now the communication between these clients and servers become very easy. DCOM and RMI are proprietary solutions from Microsoft and Sun Microsystems respectively. The idea or the objective is the same, only the implementation design varies. So in the case of RMI, you see that there is an RMI registry which acts like a advertiser, which says that, okay, here are all the services that are available from this server. And any client first talks to the RMI registry, understands what are those services that are available, gets a reference to those services, and then these references are essentially pointing to the RMI server. So the client then directly contacts the RMI server and gets those services serviced. So pretty simple, straightforward example. Let's assume the web servers don't exist for now. We have not yet discussed web servers, but the idea here is that the same services can also be exposed through web servers over the internet. We'll talk about it as our next agenda item. Okay, so that was CORBA, RMI, and DCOM. The crux or the core objective of today's lecture is to discuss web services. So what are web services? So we are still interested in building applications which span multiple distributed systems, and these distributed systems need to talk to each other, and we need some means of interoperability. So so we all understand what a web is. So I'll skip through this part, and all we mean by a service is just a software component that can be accessed through some endpoint. Okay. Let me skip these content for the sake of time. Okay, the whole idea, the way the web developed or web evolved was something like this. Initially, we had what we know as static web pages. These are just a bunch of HTMLs lying on a web server. So you say http://vvtesh.co.in, and it responds with an HTML file which I had placed there. So the web server's job is just to take an HTML page and return it. But this was very limited, and very soon we figured out that we need some more functionality, like doing or generating this HTML code dynamically to be able to connect to databases and so on. So that was the birth of dynamic web. There's several servers which became popular, like Tomcat, Glassfish, and so on, which allowed all these stuff. The history dates back to Common Gateway Interface, CGI scripts. So CGI Perl looked something like this. Essentially, you are, instead of statically typing out the HTML, now you are programmatically generating the HTML. Why is this interesting? It's interesting because now you could do validations like, let's say you have a username, password to be validated against a database. Now you could write the code which could connect to the database and do such kind of validation. The technologies evolved. So we had server-side JavaScript. So you could do something similar using JavaScript. Then Microsoft came up with ASP, Active Server Pages. Again, the idea is the same. So here you see in the top few lines, we are basically connecting to a database, retrieving some data and then validating or running a select statement over that, for instance. So that's what we are doing over here. So there are numerous technologies over here. I don't expect you to know CGI, Perl, or ASP in this course, but what I want you to appreciate is that we can now generate beautiful web pages dynamically using these kind of scripted languages. Okay, so let's move on. So this marked the beginning of the idea of software as a service. Now that I have an endpoint in the form of an app server, so any server that could serve more than an HTML page, which is able to run these kind of scripted content, is called an application server, or in short, app servers. So now that we had these kind of app server endpoints, we could now build services and then expose them for other people to use. So that was what was called as the software as a service. So here's a simple example from the Oxford Dictionary's website. So let's say I want to look up the meaning of a word like ubiquitous. So all I have to do is to put that word at the end and fire this API. So now this is a service which Oxford Dictionaries provide, and you will see a response in the JSON format, something like this on the right side, which gives you the definitions. So here it says it's present, appearing, or found anywhere. Now that we have these kind of service available, you can now put this into your application. So if you have to build a new application which requires looking up a dictionary, then you don't have to worry about building a dictionary, maintaining a dictionary. You may just invoke an API such as this and then worry about the rest of your application. So that's how the software as a service made our life really easy. Let's move on. Okay, the interesting development in the domain of web services was of REST API. So if you had followed some of the previous class presentations, we have briefly touched upon the idea of REST. REST is representational state transfer, proposed by Roy Fielding in 2000. So what are we trying to do over here? The key idea is that we want to see everything as a resource. So we want to keep resource as a first class entity in everything that we are trying to do, basically in this communication between clients and server. So there are resources which are defined, and these resources are moved around between clients and server. So talking about the same example of ubiquitous, so I'm interested in looking up the meaning of ubiquitous, right? So that's what a client wants to do. That's why the client talks to a server. So this can be generalized and said to be that the client is requesting a resource from a server, and the server transfers the representation of the state of that resource. Let's try to understand each of these. So as I said, there are three interesting things that you should note. The first thing is, of course, the idea of resource. Resource could be anything: document, image, a word whose meaning is sought. So you define what a resource is for your application. And then every resource needs to have a representation, because that's what we can transfer between the client and the server. And finally, to transfer, we need to have some standard mechanisms. So in this case, since we are talking about web services, we will leverage the web transfer protocols like the HTTP, Hypertext Transfer Protocol, and the HTTP's methods like get, post, delete, and so on to do the transfer. So here is a simple example. So this example is taken from the RESTful API.NET website, where they talk about systems configurations and devices being available on a server, and you may create a new configuration, you may retrieve the configuration, you may delete the configuration, and so on. So these are the actions the client is expected to do. So how does it happen? So we first define what we call as the URI. URI is simply these this part of the URL called /devices. Let's say. So /devices is a URI. When you combine it with the base URL, we have a uniform resource locator. So HTTP / blah 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 till the end. So this is an URL, and this is what we call as a URI. URI is uniform resource identifier. So now the idea is, if I just fire this link on a browser, by default what I'm doing is invoking the get method of the HTTP protocol. So I'm telling that I'm using HTTP protocol here. That's the first part of this URL. And when I do a get, the server understands that it's supposed to return a resource. Now to understand what resource to return to, it looks for the end. So it says I'm interested in a specific configuration, which is 678.678. So that's the ID of the resource. So it fetches that resource and returns it back to the client in a specific representation, which is designed by us, the developers. Okay, so similarly, we could do a post, put, and delete as well. So we'll talk about these. So when you do a post, you are essentially creating a new instance of the resource. So let's say you want to create a new configuration, you will do a post, and you will, along with a post request, you will submit a representation from the client end, which goes to the server. Server uses this representation to create a new instance of the resource and probably assign an ID, or even the ID is sent by the client. So it depends on the developer. And we have already seen get. Put is used to update an existing resource. So again, you send a representation with the things to be updated and just overrides the existing resource state. And of course, you can delete an instance of the resource as well. So one interesting thing to note here is that we call those HTTP methods as idempotent, which can be called many times without different outcomes. Meaning, even if you call 100 times, the state of the server does not change. So if you see here, get, put, and delete are idempotent. You keep calling them over and over again, nothing is going to change. For instance, I keep updating the same resource, let's say a particular configuration, and change the description. If I keep changing the description to a specific description 100 times, the description is going to remain the same. The state of the resource is going to remain the same. But post creates a new instance, so it is not idempotent. And when the server returns back a response, it, along with the representation, it also sends back a HTTP response code. These are all standardized. For instance, a 2xx code means that everything happened beautifully. For example, 200 is a simple OK response. You could see all these things on a browser. So if you're using Chrome, there will be something called developer tools. You may open that and then go and see the console and the network. So I have illustrated this in the Nutch presentation, which will be available online shortly. So when you, if you go to the last part, the demo part of that presentation, we open a browser and we inspect these service calls and the HTTP response codes and the JSON response that comes with this and all. So I don't want to repeat them here. I just want to bring your attention to the idea of response codes. Some response codes are very popular. For instance, 404 page not found. Whenever there is no web page existing and you fire a HTTP GET and the server could not retrieve it, server sends a 404 response back. All right. So this is what I meant. So let me see. All right, so here if you go to Chrome and open developer tools, you will see some window like this and some window like this. And if you click on any URL and go to its headers, you can see that this was the response. So this was the request URL fired and the method HTTP method was post, and this was the status code that we received from this server. You may also go and click on the response and see what response we got from the server. So for example, for this particular request, some response of this format was obtained. Yeah. So so this is how real world applications are built these days. So this is an example taken from Google News. So in order for Google News to work, so many queries are fired. It's not just single HTTP request, and for each request you could see the headers, the response, how much time it took, and so on, using the developer tools. All right, so this is the crux of today's discussion. So how do we actually design the REST API? So this is where I want you to really focus and spend most of your time. And a clear understanding of REST API designing is central to building successful web services. So there are 4 major steps. The first step is to identify the object model. Well, what do we mean by object model? So object model essentially is is to identify the resources. So we said that everything is a resource, so we are understanding what are the different kinds of resources and how they interact with each other. This is essentially your class diagram. And then the next part is to assign model URIs. So as I said, /configuration /devices. So similarly, we want to assign URIs for each resource. And then for each resource, we also need to identify a representation which depicts the state of the resource. So here I've given you an XML example which depicts the state of a device. So a device belongs to a device family. It has a OS version associated with it. There is a serial number, there's an IP address, and so on. So all this information is captured in an XML format. Representations need not be in XML all the time. It could be a JSON or it could be something else. In this case, I have used XML. And of course, finally, we need to assign HTTP methods so the transfer could happen. So let's take a banking application as an example. So let's say we want to build a banking application and we want to expose some services on the server end using REST API. So let's start identifying the object model. So if I have to build a banking application, there is an account, there is a customer, there is a teller. So all these, so this is exactly the same thing that we did in our UML class to figure out the class diagram given a scenario. That's what we did there, and that's exactly the same here as well. So given the domain requirement, you come up with an object model. So identify all the objects that are there. And now the next step, create model URIs. So for a customer, we say that there are customers, and each customer has a customer ID, and the customer ID will uniquely identify each instance of a customer. And then we say that for each customer, there are accounts. There could be multiple accounts, and account ID will identify the unique account belonging to the particular customer ID. So here you see the beauty of designing the model, designing the URIs. All right, and also remember, URIs and URLs are not the same. In some cases, a URL uniquely identifies a resource, so it may qualify as an URI, but essentially when I say URI, I mean these things like /customer ID, which uniquely identifies the resource. And when I say URL, I mean the entire http://www.google.com. So that's a URL which locates a resource in its entirety. So which means there is also a base URL component included in the URL along with the URI. All right, determine the representations. That's the third step. You may use XML, JSON, or anything else that you may like, although these two are the most popular amongst all the representation choices. So we take our customer and wonder how should the customer be represented as an XML. So you list down all the attributes of the customer that you can think of and then put them inside your XML or inside your JSON. And finally, and of course, you have to come up with the representations for every object that you have identified. And once that step is over, finally you assign an HTTP method. So you say that, all right, so here are the actions possible, like opening an account. To open an account, what I need to do is to create a new account instance on the server, and the right method to use is post. We know that post creates a new instance, so we say that HTTP post on an account, so /customer ID /account ID on this URI along with a specific representation of the account would create a new instance of account. And similarly, HTTP delete only needs a URI and it would go ahead and delete or close an account for us. So close account is the action that I want to do. HTTP delete followed by a URI is the implementation detail that would allow me to do the close account action. All right, so these are the 4 major steps that we follow in designing a REST API, and thus thus we build a web service. Now to do all this, we already have libraries and frameworks. For example, JAX-RS is a specification which tells how the Java community should come up with libraries for implementing RESTful web services. So Jersey is a popular JAX-RS implementation. So it basically enables us to implement these 4 steps that we have discussed. So how do we do that in JAX-RS? Essentially, you still do a UML model to come up with the class diagram. And once we have the class diagram which identifies the resources, then you convert them into classes. And once you have the classes, you need to tell Jersey which ones map to which URI, right? So that URI mapping is the next step. And to do that, we use annotations. And this is where JAX-RS specification comes into play. It says how you should do these annotations. And Jersey is simply an implementation which lets you do that. So for example, here we say that the path /configurations maps to this resource, configuration resource class. So whenever there is a HTTP request coming to the server with /configurations at the end, this particular class is invoked by Jersey. Now, within /configurations, if there is a /ID, then the particular get method invokes this get configuration by ID method and passes on the ID as a parameter to this method. We'll look at these things in detail in our tutorial session, but this should give you an idea of how we reached here. All right, so some closing thoughts. It's cool to have a framework which easily lets us implement the web services, but then we have to worry about how to safeguard our resources in a way. If you just expose these web services without any authentication, then people can just bombard your server with requests and can bring it down so easily. Or people who are not supposed to access it can access, and all ugly things can happen. Now, how to implement authentication? There are many ways that people have discussed. Basic HTTP authentication is you fire a request, your browser will ask for username and password. You keep you enter the username password, which is sent to the server, and the server can now deal with the password and then decide whether to serve the request or just simply send back an HTTP code, which is more appropriate. So that's one way to do it. Another way is to build this username and password in the query string. So you would have seen some query strings with question mark, user equal to ABC, and password equal to EFG. The problem with query string authentication is it's plain text, people can see it, so you want to hide it, so you have to encrypt and then put it on the query string. And also there are limitations on how long the query string can be. And recently we are moving towards API keys and token-based authentication. The idea of API keys is you first go and do a one-time registration on the server end, and server will give you an API key, which is a long, usually a 32-digit number or something like that, which you can embed in your application and send it to the server, and the server will understand that it's you, so it will allow you to do whatever you want to do. Another more secure, commonly used authentication method is the token-based authentication, which we call as the OAuth method. So this is the basic HTTP authentication. You would have seen this. Let's quickly discuss the OAuth architecture. So the client first communicates the OAuth server, which is an intermediate server between your resource server and a business client. And the OAuth server will verify the client and return an access token. So whoever has this token can now access the resource. So now the client has a token, so it will request the resource along with the token. The resource server will validate the token with the auth server, and if it says that it's a valid token, then it will return the resource. This entire diagram is called a sequence diagram. So this is another UML diagram which talks about the interactions between the object instances. So each of these is an object, an instance of class, and this is the lifeline of the object, as we say it. So this business client is requesting an access token, and it gets served at this point of time. So from here to here, some time units are passed, and till here there is nothing happening on the business and on the resource server side. So you have a dotted line over here, and auth server invokes a method on itself called the verify client. So you see a self loop here on the lifeline of the auth server, and auth server returns the token, access token over here. So this is where it is getting it. So, but the business client is still active. It then requests, so the gap between this and this is insignificant. It doesn't matter whether it was here or it was here, as long as there's nothing in between. We just say that this request happened after receiving this response. All right, and you see that auth server shuts down after this part, meaning it's not active. So let's not use the word shutdown. Let's say it's not active. After it gives the user consent, its job is over. And again, when the resource server wants to validate, again the auth server comes up and again it's alive, it does something, and then it returns the response. That's why you see two different time events here. All right, so this is what we call as a sequence diagram. You should be able to understand and draw some sequence diagrams to explain how the communication would happen between objects. And as I said, if you are careless, it's possible that people may bombard your server and get your server down. To avoid that, we do something called rate limiting. Rate limiting is essentially, a contract between the server and its users to say that, look, I'm going to service only these many requests per second, and that's to safeguard myself. There are many different approaches to do that. Leaky bucket solution is one where, so assume you have a bucket with a small hole at the bottom. So now it doesn't matter how much water you pour into it, the rate at which the water comes out of the bucket is fixed, right? So this idea can be used for rate limiting also. So lots of requests may come from the users All of them are queued up, and the queue is serviced at a specific rate. That's the idea of a leaky bucket solution. And there's also this fixed window approach. In the fixed window approach, every request is served in a fixed time slot. So it's like, you go for passport renewal to a passport office. There is a window in which you have to go and give your application. The window is open only for, let's say, half an hour. And in that half an hour, you have to go and give your, so if you are able to reach the window in that time slot, you are lucky. Otherwise, you don't get your passport request served. So that's the same idea here. So anything that exceeds the threshold is just discarded, needless to say. So here is the example where you have all the requests coming to a load balancer. Load balancer is a component which can decide, okay, which node should get the request. So it forwards the request to node 1 or node 2, and look at these as counters, and so these people would service these requests. Let's say we have already seen what Redis is. It's a key value store which keeps track of, let's say, the count of how many people are up the queue or how many they have serviced, and there could be a threshold, and it may say that this window gets closed after I after I serve these many requests or things like that. So such kind of things can be implemented, and usually key value stores are heavily used for these purposes because they are fast. Okay, so putting it all together, if you have to build a huge application such as Google News, which is essentially a large and complex system talking to multiple distributed systems, then web services seem to be a very nice way to tackle this problem of interoperability. So we have standard libraries and mechanisms to fall back and to make our life easier and simpler. I'll skip these slides on private and public cloud and leave them for you to self-read. We had discussed these as part of one of our class presentations as well. Thank you.